Okay, and well, welcome to this afternoon's BOF on monitoring. What's happened to the presentation? Okay. This was listed in the programme as being a Scampi BOF, and I just want to say very briefly, tell you a little bit about the Scampi project before we move into the main presentations. Scampi is a 30-month project within the IST programme of the European Community to develop a scalable monitoring platform for internet traffic. And it's one of the other activities is to promote the use of monitoring tools for the use of ISPs and end sites. This is a project that started in April 2002, so it's been running now for just over a year, and it's planned to run now for about another 18 months. It comprises 10 partners from the commercial, research and academic sectors. Trainer is the coordinating partner, and then you have a number of research institutes, Forth, IMEC, University of Leiden. Then there are a couple of NRENs, Chestnet and Uninet, 2 ISPs, Forthnet and Neticos, and then there's a commercial 2 commercial companies, Siemens, who I think most people would know, and a small hardware integrator in Greece called 4Plus. So the goal of the project is to develop a high-performance hardware adapter which will run or monitor up to speeds of 10 gigabits per second. And the idea is to utilize the standard PC architecture. So what we're doing is building a PCI-based card which will slot into a standard PC, and you can run normal operating systems and applications on top of the operating systems. But then the hardware adapter will provide much of the intelligence. So we're aiming at on building on top of the hardware adapter a sort of common API platform, so you can write applications standard applications that will work firstly with this card, but also we tend to port this API to a number of other platforms, such as Juniper routers. There's also some ideas for other cards. There's an Intel IXP platform and a standard Ethernet adapter. On top of this, we'll develop a number of tools, which include denial of service detection, SLS auditing, quality of service, traffic engineering. But again, some of this will be covered in the BOF itself. More information, you can find out all about the Scampi project on the Scampi website. The URL is given there. But really, we don't really want to talk specific characteristics of the Scampi project. We think that it's of more interest to most people to bring out some of the results and some of our research that we've done, which will appeal to a wider audience. So we've selected 3 topics that we think will be of interest to most of you, and we'll present those and hopefully get some feedback on that as well. The aim is for this to be a sort of slightly interactive, so please feel free to interrupt and ask questions during the presentations, because I think we would appreciate some feedback on some of these topics. So I think we move on to the first presentation, which is on denial of service detection. That will be presented by Vasilios Siris, and he works for Forth in Greece.
Thank you.
work that we've been doing in the area that maybe the sound is.
Denial of service and anomaly detection. Okay. And overview of what I'll be talking about. First of all, I'll, of course, discuss the problem, and most importantly, why it's difficult. One of the objectives, and generally when one discusses denial of service, one can think of very simple schemes like threshold-based schemes that can easily detect a denial of service attack, because denial of service attacks incorporate a huge increase of the flow rate. What I'll try to do is try to discuss how and why these simple schemes fail. And that's what I'll be doing, considering two algorithms. So the simple threshold scheme fails for one reason, because you have, in general, regular fluctuations of the traffic. But you can take into account these regular fluctuations by adaptively changing the threshold. But even then, you don't get a scheme that actually works very well. And I'll try to discuss why. And further on, I'll discuss another algorithm, which interestingly is as simple as the first one, but has much better performance and higher robustness to different attack types. And the results I'll be presenting are on SYN attack detection, which is one of the most found denial of service attacks that you see in practice. And then I'll conclude with the summary of our results and some of the future work we're planning to do. So denial of service, the aim is to prevent some users, legitimate users, from receiving some service with some specific minimum performance. How this is achieved? By consuming the resources that are available. And this can include bandwidth, memory, router forwarding capacity, DNS naming services, etc. How this is done is with flooding. So why is it important? It's important, obviously, everyone must have heard about the 2000 attack, denial of service attack on these companies. But there are still an increasing number of these incidents. As of very recent attacks on the root servers last October, or other attacks to Dolnet one can mention, but there's also a very recent and very informative survey of the CSI Institute, which indicates a very large increase in the number of these attacks. Now, the problem that we're dealing with is detection. And detection is only one of the sub-problems of denial of service. The other is, of course, prevention and reaction. Once you detect something, what do you do about it? And, of course, later on, you want to identify the attackers also. So our focus is on detecting the denial of service attacks. And more specifically, we want to do this in an early and reliable way. And one interesting thing is we're not interested only in attacks which have a very large intensity, but also can have a small intensity. And one reason why this might be interesting is the following. The way a denial of service, a distributed denial of service attack works is the following. The attacker compromises some number of hosts, which later sends some amount of traffic to some victim. So the volume here is what causes the disruption of the service. And this obviously is the aggregation of flows from a number of sources. Now, one thing one can do to detect denial of service, distributed denial of service attacks, is to measure at this point, near the victim. But also one can think of schemes that do the measurements close to these daemons, compromised hosts here. And there the flow rate is much lower than what it is at this point here. So that's one of the reasons that we're interested in identifying attacks that have a low intensity. Approaches. as I indicated in the beginning, what one generally tries to do when he does anomaly detection is try to set an alarm when the behavior deviates from the normal behavior. So the question now is, what do we identify as normal behavior? And this can either be specified beforehand, like the threshold scheme that I just mentioned, or it can be learned somehow adaptively, dynamically. And you have a number of schemes here that can measure, for example, the mean or standard deviation, or other time series analysis schemes like change point detection, which is actually one of the schemes that I'll be considering, the Q-sum cumulative sum algorithm. And as I said, this work, although the examples are for SYN attack detections, we're trying to apply them in general to anomaly detection. And I'll mention some things at the end of this talk. So why do fixed threshold schemes don't work? Well, because of the normal or regular behavior one usually sees in traffic streams. High intensity of normal traffic during the daytime, low during the nighttime. So a fixed threshold scheme doesn't work. We can't simply say when the volume is or the rate is exceeds the 0.7 mark, we have an alarm. Now, of course, what you can do to take into account these regular changes of the traffic is to adaptively set the threshold. And this is actually what I'll be trying to do in this scheme, the first scheme that I'll be discussing. Now, as I said, our focus is not only on intense attacks with a high rate of injected traffic by the attackers, but also on lower rate schemes. Now, in the previous scheme, this slide here, if I left this slide on top and you viewed it for a few seconds, it'd be easy for you to identify where the attacks arise, the areas where these peaks arise. But and this is the attacks themselves. But this is relatively simple. We're trying to do something more difficult. In other words, to have more subtle, low-intensity attacks. Now, the second graph that you see here does contain an attack, but it would take you a lot of time to see the differences, so they're not immediately evident. And it's mostly on these types of attacks that we want to develop algorithms that reliably detect them. So, what do we measure? Obviously, there are a number of variables one can measure. The aggregate traffic volume, the traffic volume per flow, or the number of requests, TCP requests. And this is actually the experiments that we've conducted are based on this. One can also measure the inter-arrival time of requests and other measures. So there are a number of things that one can measure. And obviously, it depends on the particular characteristics of the attack, which is the most appropriate variable. What statistic? One can think of the mean rate, variance, covariance, Hurst parameter, and when to measure. In the experiments that I'll present, we've conducted measurements of the number of TCP SYN requests in an interval of 10, actually should be seconds. There. So, as I said in the beginning, we consider two algorithms. The first algorithm is, let's say, a simple algorithm that one can think of. And as I said, this algorithm adaptively sets the threshold. And how it does this, it measures the mean in some previous time window. I'll explain it later, exactly how it does this. But it sets the alarm when the percentage of the traffic rate that we're actually observing in some instance is some percentage larger than this mean. And the other algorithm that I'll be discussing, the Q-sum algorithm, again tries to measure adaptively the mean rate, but it considers a different approach into what to measure and what to compare this measurement with in order to signal an alarm. So Let's go to the example here. So this is the traffic stream. This is the horizontal axis is the time. The other axis is the amount of traffic injected, number of SYN packets, and this varies, of course. And the adaptive threshold scheme tries to measure in a previous time window the mean rate and considers a threshold which is some percentage of this mean rate, where the beta parameter can be something larger than 1. And in the simple version, an alarm is set when the current rate that is measured in the current time window exceeds this amount. A more robust scheme would be to require that this exceeding the threshold continues to occur for some k number of time slots. So I measure the traffic, and when the traffic exceeds some percentage of the normal traffic for some k intervals, I set an alarm. A simple scheme. Now, the other scheme that I'll be discussing is based on hypothesis testing. Now, intuitively, what does this mean? This takes, for example, two hypotheses. The first hypothesis says that there's no attack. The other one, that there is an attack. And it tries to see the probability of one of the hypotheses over the other. And mathematically, how that is achieved is through this ratio. So this probability is the probability that there is an attack. This on the denominator is the probability that there isn't an attack. And what I do is I sum the logarithms of this ratio. And when this sum exceeds some threshold, then I hit an alarm. Now, another way to view this, and possibly a more intuitive way of how the algorithm works, is that the algorithm does nothing more than a weighted sum of the traffic, the amount of traffic, see in this yellow here circle, psi underscore t is the amount of traffic injected, minus this here is just a factor that depends on the mean rate. So you can see that this difference is what more than the factor that depends on the mean rate the user is sending. And what I do is take the weighted sum of this factor. And when this sum exceeds some threshold, I hit an alarm. Graphically, what the algorithm does is the following. As before, we have measurements of the rate. And when the rate exceeds this factor that depends on the mean rate, I start to accumulate how much more than this factor is being injected. And in other words, I sum all these dark red areas here, and this is exactly the volume or G underscore I that was appeared in the previous graph. And when this volume exceeds some threshold, I hit an alarm. So you can understand intuitively the differences between the two algorithms. This, in some sense, doesn't seek to fix a threshold above which I signify that this is a potential attack. What I do is somehow I have a memory. I accumulate how much more volume than what is usually in normal circumstances injected. And when this volume, total volume, aggregated, exceeds a threshold, then I hit an alarm. As I said, there are different types of attacks. We'll be focusing on the TCP SYN attacks, and those exploit the behavior, the three-way handshake of TCP. In other words, there's a SYN packet sent by the sender to the receiver. He replies with a SYN packet, which also acknowledges the previous SYN packet, and then a final acknowledgement by the sender completes the three-way handshake. And in a denial of service attack, the sender simply sends SYN packets to the receiver without replying to the SYN ACK packets it receives. Now, performance. How do we compare the algorithms? Obviously, what we want to do is have a high attack detection ratio. We also want a low false alarm ratio. But we're also interested in the delay. how, that is, from the time an attack begins until the time I've detected or set the alarm of the attack. But also important is the robustness of the algorithm. In other words, if the attack characteristics change, does the algorithm perform equally well or worse? Another thing is each of the algorithms, I passed them very quickly, but if you recall some of them, they have some parameters. How do I set these parameters? Obviously, these parameters affect the performance. And as we'll see, there's a trade-off between these performance measures that I mentioned in the beginning, the detection ratio, false alarm rate, and detection delay. So one of the objectives of the work that I'll be presenting right now is to evaluate these previous algorithms that I just mentioned for attacks with different characteristics in order to understand exactly how the parameters of the algorithm affect their performance. And mostly the characteristics are the intensity of the attack, that is the rate of the SYN packets that are injected by the attacker, but also if we assume that the attack doesn't jump immediately to this peak rate but slowly increases the rate, that's another parameter that one can consider. The experiments were conducted as follows. We took a real traffic trace, 11 hours. We aggregated the number of packets, SYN packets received in 10-second intervals. And in the experiments, we had the synthetic attacks, as I explained before. That is, there's some time to reach the peak value, and then at the peak value gives another parameter. And if we add some robustness, so things are not deterministic, in the experiments, we add some robustness and we get the form of the attacks. And there are a number of other parameters I won't discuss. Each of the results was for 50 runs with a 95% confidence interval. So the first scheme, the adaptive threshold scheme, works very well, as you can see from the last graph here. So the first graph is the trace, second trace plus attack, third is the attack, and the last one is when the alarms are triggered by the particular algorithm. So more or less you see when we're in the red zone here, an alarm is set. Of course, there are some areas where an alarm is set even when I'm not in this, the red zone, and that's a false positive. And this is for a relatively large, as you can see, peak rate here of the red graph, and in particular 250% of the mean. So the Q-sum also works very well for such attack types. Now what happens if we decrease the peak of the packets, the SYN packets that the attacker sends? How do the two algorithms perform? Well, this is the case for the adaptive threshold algorithm, and you can see that the attacks now, the red lines, are much lower. And this leads to a very bad behavior of the algorithm. On the other hand, for the Q-sum algorithm, well, that behaves more or less as before. That is, it's much more robust to attacks that have a very smaller intensity, a smaller peak of injected traffic. Now, this, as I said before, a particularly important thing is how to tune the parameters. So in this graph, I show how the behavior, the performance of the Q-sum parameter depends on the threshold of when to signal an alarm. And as you can see, as this threshold increases, well, more or less the detection probability remains 100%, whereas the false alarm ratio decreases. And this is also the case with the adaptive threshold scheme, but for large amplitude attacks. Another way to view the results, as I said in the beginning, it's not only the detection probability that matters, but it's also the trade-off. That is, we trade off some detection probability for a better, let's say, or a smaller false alarm ratio. And that could be viewed in a graph such as the ones that I present here. In the horizontal axis is the detection probability. In the other axis, the vertical, is the false alarm ratio. And the different points here are for different variables of the parameter of the algorithm. And here's the adaptive threshold algorithm. And you can see I can trade off, I can decrease the false alarm ratio, but when I approach the one here, then the detection probability starts to decrease. So that's the trade-off I've been mentioning. And the better, an algorithm works better if I'm very close to this point here, the lower right of the graphs. And, well, the QSUM algorithm has even better performance if you compare the two. This was for a high-intensity attack. What happens with a low-intensity attack? And as I said, the adaptive threshold algorithm has worse performance, and this is shown in the fact that the points here now are shifted, let's say, towards the left. That is, I can't achieve a very high, let's say, probability, detection probability, but also a low false alarm ratio. Whereas the QSUM, you see, it's more closer to this point here, which means that it's better in terms of this trade-off between detection probability and false alarm rate. And another graph that shows this dependence and why the first algorithm, the adaptive threshold, doesn't perform that well. Here, the blue line, detection probability, the red line is the false alarm ratio, and you see at some point when the detection the false alarm rate, is very, starts to get low, also the detection probability leaves the 100% mark. So that's the trade-off. I can't achieve a very small false alarm ratio while at the same time maintain a high detection probability. With what? With this algorithm here. Another, and this will be the final result that I'll be presenting, the detection delay is also important. And this graph shows the trade-off between false alarm ratio, and this is the vertical axis here, and detection delay. So the better is when I'm close to this point here, the lower left one. And as I said, the different attack characteristics can affect the performance of our algorithm. And whereas this graph, the attacker immediately jumps to the peak rate with which he injects traffic, in this lower graph here, the attacker slowly, or I should say it's the other way around. In this graph, the attacker jumps to the peak rate, whereas in the top graph, the attacker slowly increases his peak rate. And you can see in the second case, that is slowly increasing his peak rate, results in a comparatively larger delay. That's why this graph, compared to this graph, is shifted towards the right, compared to the bottom graph. So this is another way one can present the results that, again, visualize the trade-off between false alarm ratio and detection delay. So in summary, what have our results indicated? Well, first of all, the performance, as I said, depends on the attack characteristics. Obviously, for some types of attacks, and in particular for intense attacks, which have a high peak rate of attack traffic, one can think of straightforward procedures that work very well. But they're not robust for different attack types. And I showed you one example of a non-robust scheme, which is not robust for a low intensity of attacks. But I also showed that a scheme that is based on some well-defined statistical change point detection theory can be equally robust, high performance, but is not necessarily complex. One thing that people are afraid of is that if they base the algorithms on some statistical models, they'll end up with something highly complex. This is not true. And I tried to show you why this is not true. Essentially, you take with the QSUM algorithm the weighted sum of a volume, which is simple. And again, the results, and something that is important is how the parameters affect the performance, and that's important because you need to tune the parameters. Some future work. Of course, one thing that can be done is to apply these algorithms to other measures, other statistics, and also try to combine alarms between different statistics. But also another idea is to apply it to quality of service measurements in order to have an early detection of when the quality of service will degrade. In other words, one can think of, for example, the delay as a measurement. And up to now, how does the quality of service monitoring work? It checks the delay, and if the delay exceeds some threshold, it hits an alarm. Well, what one can do is the following. Apply to the measurements of the delay algorithms such as the ones that I mentioned. And even before the delay threshold is violated, one can get some indication of imminent warnings of quality of service violations based on changes in the normal behavior of the measure at hand here, which is the delay. So this is some ideas that we're currently looking into. So I think that completes my talk. Thank you for listening, and I'll be happy to answer any questions you have.
Could you make some comment about the tool itself? About the tool itself, the technique. With which tool did you measure number of SYN packets, and is this process CPU consuming, or are you able to measure it on I don't know, gigabit interface or something? Okay, that brings into the other work that is done within this project. That this work is being done, the SCAMBI project, which looks into these problems. But my answer would be, for this type of algorithms, denial of service, what you need is, in 10 seconds, you need aggregate measurements of some variable, for example, of number of SYN packets. So they're relatively, let's say, lightweight in terms of the requirements they impose on the measurement infrastructure. This does not mean that one can not try to run the algorithm on a smaller time scales. But even in this time scales, the algorithms seem to work. But this, as I said before, does not mean that the requirements of all applications that require measurements are of this nature.
In fact, you almost took my question, but can you say a few words more about the application itself? I mean, is it based on net flow data? How it's developed? Is it possible to look at the application? I mean, is there a beta version available, something like this on the website? Or?
Well, what we needed here is just a trace which had, as I said before, in 10-second intervals, the number of SYN packets. Now, this can be gotten either from NetFlow, if you like, and if it has the ability to give these measurements, or from another more high performance adapter that's able to measure at gigabit links. But the input requirements are, as I said again, 10 seconds volume in consecutive intervals of that duration. Okay, thank you.
Okay, thank you, Vasilis, once again. Okay, we'll move on to our second presentation this afternoon, which will be given by Luca Deri of Neticos in Italy. And he will be talking about monitoring networks at gigabit speeds.
you don't mind. Okay, tonight I want to describe you what we have done in Pisa about passive network monitoring. The problem is the following. We have a network that is running at 1 gigabit per second, and we want to see what's flowing inside the network. On the other hand, we are not able to invest a lot of money in monitoring tools because, as you know, both hardware and software are quite expensive. But we have decided to follow a different approach. We have decided to build the network from scratch, okay, thinking in terms of network monitoring, because at high speeds, it makes even more sense to see what's flowing through your network. At lower speed, as somebody pointed out this morning, okay, there is no need because you know what's passing through. So we decided to build the network thinking about network monitoring. So today I'm going to show you something about the issues that we are facing with when we plan to monitor at high speed. Because when you go at 100 megabit, more or less you have no problem with the current CPU power you can get. But when you go above 1 gig or more, then you run into trouble. And you run more into trouble when you have an attack in progress, because at that point you have to handle many more packets than what you are usually handling. So therefore we have somehow to handle some filtering. So we want to filter out the traffic that we are not interested in and to analyze only a portion of the traffic. And also we need some protocol conversion, because as you know, the links are basically based on Ethernet for the local network, but for the long-run links, they're probably based on ATM, SDH, SONET, something that is not IP. IP is running, encapsulating in some packets that flow across this network. And because we only speak IP, we are interested only in IP, we must convert somehow, we must extract the IP part of the packet out of ATM, out of SONET. And once we have done that, we must capture the packets, so make sure that we are able to capture all, or at least most of the packets that are flowing to our network, and classify them. So what are the issues? Basically, when you want to work at 100 megabit or less, you have no major problems. You take libpickup, you create your application, and you're done. Most of the sniffers or traffic analysis applications use this library that is part of the operating system, and that's all. The problem is that when you want to go a step further, then you have two kinds of problems. First of all, the availability of the interface on your PC, because as I've said, it's quite easy to go to a shop and buy an Ethernet interface. It is totally different story to buy an ATM interface for a PC. And suppose you can do that, or suppose you can afford to do that, then you have the problem of extracting the IP packet. And that's not a secondary issue. The other problem is that today's PCs are not fast enough to capture all the packets, move those packets to memory, and then from the kernel memory to the application level, and then to analyze them. So we have here another problem. Modern PCI bus that runs with 64-bit wide and 66 megahertz can help, but is definitely limited. So we cannot do much. But this is fast enough for running at 1 gig. So what is our approach? First of all, we want to build a network using intelligent routers. Because we had to build a network, we decided to use the Juniper M-series boxes. I'm not representing Juniper here, but what I want to say is the following. If you have a fast network, it's very important to know what's passing into the network. And those boxes are able to help us a lot. I will show you why. And they basically are we delegate to the box a part of the work we should do with normal tools on software on the computer. So we want to have an intelligent router. Then we want to use a normal PC. A normal PC you can buy at the shop based on x86. We tend to use dual processor because they perform much better when you have a lot of traffic. We want to use a free operating system like Linux and FreeBSD. And of course, we need gigabit cards, okay, running at with a 64-bit PCI. We decided to use the Intel because we think they are quite reliable, they are quite good. So the goals are, first of all, speed 1 gig, okay, for the moment. Passive network monitoring, I want to avoid losing packets or lose very little. 2, we want to generate traffic information, okay, in a format that everybody can understand. A very common format is NetFlow. I will talk about NetFlow later. We want to be able to monitor both IPv4 and IPv6. NetFlow speaks IPv4 only. So that's why we have decided to use NFlow. And we want to know performance data and accounting data. So these are the goals. I will show you now what we have done and what we have achieved. Basically, the architecture is the following. We have our network, and we have the internet. On the border gateway, in the Juniper, we are mirroring this traffic onto a gigabit Ethernet link. This one can be anything. Probably this one is 1 gig Ethernet. Above, you will have Sonnet or ATM, or even more links that are going towards the internet. And we monitor basically this here. So the incoming and the outgoing traffic. Here we have connected one PC that has 1 gigabit Ethernet interface directly to the Juniper box. And this one runs one software called mprobe I have developed that generates NetFlow records. Those records are sent to another machine that runs another software I've developed called ntop that receives those flows and shows you some information. For statistical or for historical data analysis, we have decided to save those records into a format that is very common named RRG. So, problem number 1, filtering. We want to filter the packets. If we have a lot of traffic, we want to focus only on the traffic we are interested in, probably because in our big network we have a lot of traffic that does not belong to us, so we want to remove this traffic. We don't want to overflow the machine with this traffic. If we filter on the machine, on the PC, basically we have to send a lot of traffic and to discard traffic. This means that we have to do some work on the PC. But those boxes are able to do this on our behalf, and they are doing quite well at Y speed. So we don't lose anything here. The PC is not overloaded at all. Suppose that you have a 10 gig Ethernet link, and the traffic you are interested in is a few hundred kilobytes. Basically, the PC doesn't have to receive 10 gig and then filter out 10 kilobytes. But it receives 10 kilobytes because this work has been performed by the Juniper. And second, we want to do traffic mirroring. So basically, we want to forward traffic here depending on what we want to do. So we want to have this machine receive only the portion of the traffic we must analyze. Okay? So we remove this. And as I said, we need some protocol conversion because here we speak IP. So we want to be able to see IP packets. So talking about filtering, okay, the Juniper are able to filter both IPv4 and IPv6. They use BPF-like filtering terms. They are not exactly like BPF, but they look very similar. And basically, you can do the same thing like BPF is doing. Okay, basically the only exception is that with BPF you can go inside the packet payload and say, if the packet contains this, then. With Juniper you're stuck at the header, as far as I know. And then it is possible to count some traffic directly into the router, and then to read those counters using SNMP. So some measurements can already be done directly into the router. It is very simple to read those data using tools like MRTG or RDD-based tools, as I said, via SNMP. Traffic mirroring. It's important for us to do protocol conversion, so we can handle only IP, okay, and we don't have to care about ATM, Sonnet, or whatever you have. That's a problem of Juniper. Okay, with this approach, we only see IP packets. And second, we can have packet sampling, because, for instance, if you have a 10 gig line, you can tell the box to send you just a portion of the traffic, probably 1 gig, because, as I said, for the moment we have used 1 gigabit interface, because it's very, simple and cheap to buy 1 gig 64-bit PCI adapter for a PC. 10 gig adapters are much more expensive. Also, we can do multi-link mirroring. Okay, we can mirror several links onto one port. Oops. For accounting, we decided to use, as I said, NetFlow. And the box itself can do some aggregation flow support. And for complex accounting, we decided to use an external PC connected to a mirror port. Okay, I just want to show you now a very short demo. This is a remote demo. Okay, I have modified link pickup, okay, and I put this filtering expression. So basically, link pickup has been enhanced to recognize not only BPF filters, but also Juniper filters. If you go back to the picture here, this demo application is running on this machine. Having modified link pickup is possible for every link pickup based application. So basically, most of the sniffer, most of the traffic analyzer, to go into the Juniper and set the filter. So in this case, the filter is evaluated not on the local machine, but directly into the box. This is a remote demo. So I modify link pickup, and when TCP dump starts, sets the filter into the box and sends me everything. Okay, this is mostly SSH traffic because I'm connected remotely to the machine. This is basically the code. Okay, I have enhanced the link pickup. If it sees less than something greater than, this filter is sent to this box. So we have juniper.neticos.com. So this filter is sent to this Juniper box, and then TCP dump starts. So the filter is not evaluated into the local machine, but on the remote machine. I'll show you, for instance, another demo. So this one sets protocol UDP, so we filter UDP packets directly into the Juniper box. So the Juniper box sends to TCP dump only those packets. See, when it starts, it opens a session with XML RPC with the box. And now, as you can see, we only see UDP. So with respect to filtering, Juniper is great because we can filter everything directly into the box. So now TCP dump does not receive the full flow of packets you have seen before, okay? But just receive a sub-portion of it. All this code is available as part of the NTOP application. If you go to ntop.org, you download NTOP, there is a directory called utils and Juniper, and you will find the code that we have developed for doing this. So filtering is performed in hardware at wide speed directly into the box. Okay, now suppose that we have filtered the traffic and that our application receives the traffic we are interested in. So we have to filter and to classify this information. So first problem, capture. As I said, it's very easy to capture at 100 megabit. At 1 gig and above, it's a problem. Okay, mostly because the packets have to be copied from the network interface to the kernel and up. We said we want to rely on NetFlow. Unfortunately, NetFlow implementations are not great. In fact, most of the vendors cannot handle more than 10,000 packets per second per NetFlow. So this means that the box is able probably to switch 1 million packets per second, but just as a portion of it is used for generating flows. And this is a problem. On some other boxes, for instance, all those based on CPU, if you enable NetFlow, you must make sure that your router has enough CPU for routing the packets. And also, we would like to do some flow collection. So basically, in the box that's connected directly to the Juniper, this is what's happening. The packet arrives, is sent above to the normal stack, then to the BPF driver, and here we have our applications. So the application captures the packet and generates the flow, because I've said we cannot rely on the flow generation inside the box, because it's not fast enough for our purposes. The problem with lib pickup is, first of all, there are multiple packet copies, okay? And then there is a very costly data exchange from the card to the kernel to the user application, because every packet has to be sent out up to the application space. Therefore, there is a severe packet loss if the user-land application cannot cope with the kernel, especially if your network is overloaded. The user-land application don't have enough time, so they cannot handle the packets. This is a problem. So what we have done in order to enhance this, to go even further, is the following. We have written a module for the moment for Linux, and we are testing it on BSD, that does this. Takes the packet is copied into a circular buffer, and the application, the sniffer, or in the case the NetFlow application, talks directly with the circular buffer using mmap. So basically, this is a sort of shared memory. The circular buffer is shared, the kernel shares it with the sniffer. So you have one memory, no copies at all, beside the copy of the packet to the circular buffer. The application then is free to fetch packets in a way similar to this, okay? We do a map, so we map the buffer, and then we do a select. If there is a packet, we take the packet, we do something with the packet, then we move to the next slot. This one, in theory, should be faster than lib pickup, because with lib pickup, I have a lot of system calls. Every time I want to get a packet, I have to interrupt my program, go into the kernel, and then the kernel says, okay, now you have the packet, get it. Here, I have just select, and then here, basically, he's pointing to the packet buffer I got before. Okay. Unfortunately, links are not working that way. In fact, the performance improvement is very little with respect to lib pickup. And the reason is the following. First of all, okay, it's very fast to take the packet and copy it to the buffer. But then this packet somehow stays into the kernel, and the application has to do a sort of polling. Okay, so we call select. The thing is that select costs a lot in a fast network, because in a fast network, packets are sent very quickly. So therefore, calling select makes us spend a lot of time. So it's much better to have something like, for instance, smart select. We call select. As soon as we have one packet, we don't call select again, but we try to read the second packet. And as long as we have a packet, we continue. And as soon as we don't have a packet to read, we call select. And this one has improved things a little bit. Okay, but it's not really great, because as I said, we have a 10% improvement with respect to pickup. So it's not the case to create a kernel module, install the module, run your application for improving 10%. So we have done active polling. So we do an infinite loop. Okay, is there a packet? Yes. Get the packet. No packet. Again. So we go back. Basically, we don't call this select. We just check if there is a packet. No packet. We call while again. This one uses a lot of CPU. Okay, but don't forget that if you have a lot to read, so if you have a very fast network, the application, so the user-land application doesn't get a lot of CPU cycles, because most of the cycles are used by the kernel. So those workarounds improve the situation a little bit, but they're not really great. This is basically explained very well in Luigi Rizzo's homepage. So the drawback is that, okay, we are faster capturing packets, storing packets into the kernel, but then it's very slow taking the packets out of the kernel. So therefore, we are losing packets. So what we have done with solution number 2 is to do everything into the kernel. So we handle packets into the kernel, we create flows, and then we move flows to the user land over this shared memory. This one increases a lot the performance, because packets and flows are not the same. Basically, you have a lot of packets for one flow. So one flow contains a lot of packets. So therefore, if you have a very long file transfer, you will see one flow in one direction, one flow in the other direction, instead of seeing, I don't know, 100,000 of packets that belong to this flow. And then the user land application with some code that is similar to this will move here, not a packet, but the net flow that has been created directly into the kernel by our module. So basically here, we exchange on the circular buffer the flows. And at this point, we can spend some time with select, with doing active polling, because here, we don't have so many packets to move up, but we have very little packet to move. So we have seen a strong performance improvement. So doing everything into the kernel is much better. We have basically no copy of the packet from the NIC to the kernel to the user land, because for good cards, the packet stays into the NIC. The kernel has a reference pointer to it, and then the kernel module I have developed takes this packet, increments something, and doesn't copy the packet up, because as I said, up we send only the flows. We have basically no packet loss, because we can run as fast as the machine can run. Okay? Every time there's an interrupt, we take the packet, we do something, and that's it. And basically, the speed limit is limited by the CPU speed, by how fast this kernel and this CPU is able to handle packets. And also, the user land application that reads the flow is very simple, because it has to read the flow and send it by UDP to other collectors. Okay, this is one aspect, packet collection. Then we want to export this information to the application. As I said, NetFlow somehow is not enough for us, because it doesn't contain everything we need. So we have defined a new flow information model called nflow, www.nflow.org, that features this. First of all, the addresses can be specified in both IPv4 and IPv6. So you can have both. NetFlow is limited to IPv4. We added some space for VLAN tagging and MPLS label. So we are able to export this information to the user land application. We have some room for performance, both of the network and the application, and for passive fingerprinting information. Also, we compress the flows. So for instance, with NetFlow v5, you're able to put into one UDP packet 30 flows. Here, you can put at least double of them using compression based on gzip. Also, you have no repudiation, because into the NetFlow flows, we put a shared key, we calculate the digest, we remove the shared key, and we put the digest. So when we ship the packet, we are sure that this packet is coming from the right source. It's not that somebody's forging the packet. With the old NetFlow, you have the flow counter, and that's it for you. This one is already supported by nprobe. nprobe is the software probe we have developed, and that is available under the GPL license. So basically, just to complete this talk, packet filtering and protocol conversion performed in hardware at wide speed into the Juniper box. So this is basically free for us, because we need the Juniper box for running the network, so it doesn't cost anything. The Juniper box is not enough for generating flows, because I said it cannot handle more than 7,000 packets per second. So therefore, we do accounting outside of the box. We mirror traffic. We buy a normal PC, better with 2 CPUs, and we put nprobe on it, and we generate net flows. Using, as I said, this alpha code, we are already testing it, but it's not yet good for production. With this probe, we're able to run at full speed, okay, and to overcome the limitation of the same nprobe based on pickup that cannot handle more than 250,000 packets per second, that are a huge improvement already with respect to 7,000 packets per second the vendor can offer you. So basically, this is all. If you visit the ntop.org homepage, you can download most of this stuff. Thank you.
Any questions for Luca?
Good.
Yeah, you stunned them into
Thank you.
silence. Okay, and then we'll have moved to our last presentation for this afternoon, and this is talk about something called the OK Corral, or OK Corral, I think, to pronounce it more correctly. And this has been given by Herbert Boss from the University of Leiden Institute of Computing, or something like that. Herbert? Advanced Computing, yes.
Okay. So basically this is quite appropriate after Luca's talk, because what we've been trying to do is minimize copying and minimize context switching if we can. So what we're trying to do in the Scampi project, one of the early goals of the Scampi project, was to push down as much of the processing of packets to the lowest possible processing level. So this could be a Juniper switch, or this could be your advanced new type of NIC, okay? Or, you know, in case you have a traditional hardware, this could be your kernel, okay? So the open kernel environment, or the OKI, is basically an attempt to open up all the levels of the processing hierarchy to third parties, because this is something that we'll have to deal with. If we push down a lot of processing to the lowest possible level, we need to be concerned about what that processing might do. We need to be concerned about safety. So we're trying to open up all levels of the processing hierarchy in a safe manner. Okay, all the code for the OKI, it's not .11 release, I believe, or not .12 release currently, is available from this website. Okay, so we want to allow third parties to program the lower levels of our processing hierarchy, and we want to enforce the safety by software isolation. Okay, this is not the same as software fault isolation, as I'll explain shortly. It entails a bit more than that. Okay, why do we want to do this with software-based isolation? Well, simply because we might not have the appropriate hardware support for isolating applications. Why? Because we're running at the lowest possible level already. Okay, so there are no longer any privileged instructions. We can have access to any instruction. Okay, and there might not be an MMU, etc. In fact, there might not even be an operating system. If you're running on say, a network processor, you might not have an operating system to use. Okay, so examples include the Linux kernel and, for example, network processors. Okay, at the same time, we want to use fully optimized native code for speed reasons. Okay, so no interpretation, no BPF sort of interpreted stack language or so. And we want to provide safety in terms of resource control, meaning safety in terms of CPU usage or processing time, heap, stack, API, you name it. Okay, how do we do this? Well, we basically use two key components. Explicit trust management and a trusted compiler. The trusted compiler is responsible for enforcing the safety restrictions. Okay, so we restrict the code's access to resources depending on the privileges that have been explicitly given to the application or the user by means of the trust management in terms of credentials. Okay, and we have a code loader which checks whether the code that you're about to load, the processing of packets that you want to do at a low level, actually is allowed in accordance with the policy that exists for this site. So, okay, so I'm not a system administrator, so I'll probably not be allowed to load just any code into my network processor or Linux kernel. But the system administrator might have more elaborate privileges. Okay, so the code loader basically accepts a blob of code together with authentication and a bunch of credentials which specify what sort of code this is, one, and what this code is allowed to do. And if the credentials are okay for me, so if there is some authority which authorizes me that this is okay, it loads the code. And it loads code of a specific type.
Okay, and a type in terms of in OKI terminology is with a set of resource restrictions. Okay, so for example, a type might be you are allowed to load code with a maximum heap usage of less than a megabyte. Okay, arbitrary, similar restrictions hold for CPU time, etc. Okay, then the type, so it's similar to programming language types, can be instantiated when we actually load the code or even compile the code. And it's instantiated by the parameters that I supply as a user. Okay, the parameters obviously have to be compliant with the type. Okay, but apart from that, I can specify exactly how much resources I'll be using. Okay, so the kind of restrictions that we currently have are on CPU, heap, stack, or recursion, APIs, pointers, so we cannot point it wildly into memory, and the kernel or the environment cannot point wildly into our memory space. Some support for privacy, so that when a packet comes whizzing by, maybe we are not allowed to access all the fields, and accesses to a memory bus on the network processor. Okay, so brief sketch of how this works. We have a user sitting on one side, and it actually all takes place with remote procedure calls, so it can actually sit across a network. It supplies to the compiler a tuple consisting of object source code, plain C-like source code, the credentials for this user, which specify what the user is allowed to do and what its code is allowed to do, and a policy and parameters. Okay, and the policy basically determines what sort of restrictions will be applied to this code. Okay, so what sort of CPU limitations, heap limitations, etc., can be applied to this code. Now, you're only allowed to create code, to generate code, so the OKI compiler only compiles your source code if you have the appropriate credentials for this policy that you're trying to compile it with. Okay, and then there are the parameters that I talked about, so you're able to parameterize the code. Now, when everything is hunky-dory, the OKI compiler generates normal object code, possibly with some dynamic restrictions, some dynamic checks. But hopefully it'll try to do as much as possible statically. So it generates the object code, and it generates a compilation record corresponding to that object code. Okay? The compilation record is basically tying the object code to the policy. Okay, so it's unforgeable because it's signed and it uses MD5s instead of names or anything. Okay, so basically it creates proof that this object code was created by this compiler with this set of restrictions. Okay, so the code loader then gets presented this object code, the credentials that go with the user, and the compilation record that was generated by the compiler, checks all that, and will load it into the kernel if they all match up. Okay, and it adds a little bit of support code, for example, for making sure that the processing time is restricted. This credential-based authorization that we use for the OKI may well be used for some other Scampi operations as well, because there might actually be lots of other things that you might want to restrict, such as creating flows or access to certain things, etc. The compilation record, I should mention, is just another credential. Okay, so it's basically getting coded as another keynote credentials. And the credentials are set explicitly and used transparently, meaning we have a special function call to set a bunch of authorization credentials. Okay, and after that, with any operation that requires credentials requires authorization, it will actually look at those credentials that you've specified a priori. Okay, the code loader currently does a little bit more. It also does some resource availability admission control. So it checks its database of what whether we actually have the amount of memory that this code requires, regardless of whether you're allowed to use it. If there was any of the enough capacity, it'll check if there is any enough capacity, and if so, it'll load the code. Okay, so just to have a brief look at what these credentials actually look like. They look fairly scary, but that's mostly because of the long keys that are in here. It basically says it's a keynote credential with some comments. It has an authorizer. Okay, so that's the entity that grants the privilege, grants the credential to do something. Okay, and it licenses some other party. Okay, so my system administrator, in this particular case, my system administrator might be this public key, granting me, with this public key, a number of rights. For example, to use the operation create flow within the scampi.mapi domain. Okay, provided that one of the parameters that I use in this create flow operation equals a local IP address. Okay, and it's the authorizer, my system administrator, then signs the credential, so that I can just ship it around. Don't have to worry about anybody forging it or using it on my behalf. Okay. So now, how do we do this? How do we enforce these limitations? The restrictions on resource usage are basically enforced by an environment setup code, or ASC. Okay, ASCs are automatically prepended to the user code, to the source code that I supply. Okay, it defines some runtime support. It explicitly defines the API that I'm supposed to use. Okay, so it declares the API, and it prevents me from importing other APIs. Okay, so it removes the ability to declare or import new APIs or access the private parts of this environment setup code or perform any unsafe operations. Okay, we're at an advantage over other kernel module approaches in that we can use whole program analysis. Okay, we're assuming that everything that we're about to load is compiled into a single translation unit, so we can do a whole program analysis, which helps us a little bit. Okay, so the translation unit that we end up with consists of a bunch of macro definitions that define the parameterization, the environment setup code, which consists just of a block of code, and a little bit of user code, or a lot of user code. Okay, now we realized at some point, and actually this Oki stuff started a little bit before the official Scampi starting date, but that was because the starting date of the Scampi project turned out to be a bit later than we anticipated. So from the beginning, we realized that there are many different user classes, and they all have different preferences or requirements as to the restrictions or the access to resources that they require. Okay, now one way to go about doing things is develop a special purpose language for each user class. Okay, we didn't want to do that. We think special purpose user programming languages are useful, but not in this particular case, because user classes might change, and it takes a lot of time to learn new languages. Okay, so we wanted one language that can be customized, can be restricted. Okay, and furthermore, what we required of this language was that it interfaced easily with, say, the rest of the kernel or the rest of the environment that we're dealing with. So ideally, we wanted something like C. Okay, so we ended up with a crash-free version of C known as Cyclone, which we had to modify quite extensively to make it fit our purposes. Okay, what is Cyclone? Cyclone is a strongly typed, pointer-protected, meaning you cannot, dereference null pointers, etc. Garbage collected And region-based memory protected programming language, region-based memory protection means that you cannot, for example, return a pointer in a function, return a pointer to a local variable, which would be unsafe. Okay, uses region-based memory protection. Okay, so a measure of safety that we required was provided by a combination of the existing Cyclone features and a whole bunch of new ones which we had to introduce. Okay, for example, we have spatial pointer safety, meaning that we have the Cyclone kind of pointer safety in that we cannot dereference non-nullable pointers. We have pointers that may be bounded to a specific memory area, and we have normal C pointers. Okay, normal C pointers always have to be checked. Okay, to see if they are not null dereferences or what have you. Non-nullable pointers do not incur any static checks whatsoever. Okay. By the way, the code that you generate with Cyclone looks just like C. So there's very little difficulty in learning the language. So that was spatial pointer safety. We also have implemented temporal pointer safety, which basically have something to do with region-based protection. So we use the region-based protection scheme, tying a pointer to a scope. For example, to prevent the returning of an address of a local variable. And we added a kernel region to this set of regions, okay? So that we may have pointers into the kernel and have special behavior when we have pointers into the kernel. Region-based protection and Cyclone's original garbage collector work really well when you have a Cyclone-only solution, but we have many problems if we just want to do this and interact with C code, especially C code in the kernel of an operating system. Okay, an example of this might be, you might have an OKI module, so a blob of your code with pointers to kernel memory. Okay, what happens? What happens if you try to free that memory in the kernel of which you have no knowledge? Okay, so I'm not going to explain in detail the solution that we have for that. There's papers on the website that explain this in detail. But so we have actually implemented schemes that avoid you dereferencing memory that is, trying to access memory that no longer exists. Temporal pointer safety. Okay, some other things. We are able to restrict the language by using a specific forbid construct. So, for example, we could say forbid extern C, which means we cannot import any C APIs. We can forbid a specific namespace, and we use this to forbid access to the private parts of the environment setup code, for example. Forbid catch exceptions of specific exceptions, I should say, specific types, so that user code is not able to catch any exceptions that OKI uses to kill the module. For the APIs, we have a number of things. We have API and entry point wrapping. So an entry point into the OKI is something that can be called from outside the OKI module. So from the rest of the kernel, might call a function. Okay. Now we have to be very careful. We have to wrap that so that any locks or any other problems that might arise are dealt with appropriately. And it's especially important for our stack limitation implementation. Okay, so potential entry points are explicitly declared, and we can only take pointers of those declared entry points. Okay, they're automatically wrapped always, and the flip side of this is the API of the kernel that we're trying to call. Okay, now that may or may not be wrapped. Okay, that is actually this should actually probably be a separate bullet. Kernel APIs may be wrapped also. Okay, then we have privacy. We have sensitive data protection using a locked construct, which provides us privacy at no cost, no runtime cost. Okay, so the locked construct, whenever you declare a variable locked, okay, it means that you cannot use it in calculations, and you cannot cast it to any other type. Okay, so if you declare it locked const, you cannot write to it either. Okay, this basically allows us to share parts of a struct. Okay, for example, parts of an IP header. For example, we might declare the source IP address or the destination IP address as locked const even. Okay, so normally you would do something like anonymizing at this point, but that costs cycles. Okay, so you can actually do this at no runtime cost. I'm not going to go into stack overrun protection for time reasons, but the idea is basically that you have a bunch of checkpoints, and whenever you have arrived at a checkpoint, there should be enough stack space left to arrive at all of the other checkpoints that can be reached from that checkpoint. Okay, so that is basically, if we're here, we have to make sure, regardless of which functions are called in between, that we can actually get to here. Fairly simple. And the timeout protection is the most variable part of the Oki solution, because there are multiple solutions that you might use for timeout protection. Timeout protection is basically our bound on the processing time. We want to limit, for example, the time that we hog the CPU or hog some processing engine that we're using, a micro engine, for example. Now, a simple way of doing that is have checks in all the backward jumps. Okay, the guys at University of Pennsylvania are doing this. They also have a Cyclone language running in a kernel, and they provide dynamic checks in all the backward jumps. See if they're, if you've used up your quota of instructions, and if you've used up your quota of instructions, well, you die, or I don't know what they do. Maybe they just, block you for a while. Okay, the other way of doing it, is certainly in the Linux kernel, is to abuse the timer interrupt. Okay, just simply check when you return from a timer interrupt whether or not you've exceeded your CPU time. Okay, and any other approach might exist. And for example, we've taken another approach in a study which we did on the IXP 1200 network processor. Okay, so the timer interrupt is the one that we've used on our Linux implementation. Why? Because dynamic checks incur a fairly large amount of overhead if you have loops that, maybe travel over an entire packet length. Okay, so the timer interrupt works that on return from an interrupt, we check if a timeout has been detected in any of the Oki modules. If so, we jump to a callback function that was explicitly registered by the environment setup code runtime support. Remember, there was a block of runtime support sitting on the side of the modules. And this function may then throw an exception, which means that the module that has violated its CPU time limitations will be killed. Okay, it's actually fairly cautious in when it's doing this, because the code that you're about to kill might actually currently be accessing a kernel function, in which case you cannot just kill it directly. It takes that into account. Okay, so what's the overhead of all this? Because clearly we do need some dynamic checks, but we can do a lot of this statically. So I don't have any monitoring examples, but we've used the Oki in a couple of transcoding experiments. And this is a transcoding experiment which adds forward error correction code to all the packets of going to a specific UDP port number. So the horizontal axis, the horizontal axis shows the packet size, and the vertical axis shows the time in milliseconds. Okay, so we have two versions of this. This is the OK implementation. This is an equivalent optimal implementation in plain C. Okay, no Cyclone, no Oki Cyclone, plain C. And you can see that the overhead grows a bit as the packet size grows, because it'll have to, process the entire packet length, the entire payload, and do some fairly complex computation on that. Now, we've also created a manually unrolled version of this same application, which, because we know how the Oki Cyclone compiler works, basically gets rid of all the overhead. Okay, why is this? Partly because GCC 295, which we used, didn't optimize all that well. It actually did a silly thing there. But anyway, it's just to show that we don't need a lot of overhead on this. Another example is audio resampling, which is a much simpler application. So it's much faster. Oh, take it. This is back, right? Okay. So it's a very simple resampling transcoder. We have audio packets coming in, and we throw out half of the sample, half of the samples, 50% of the samples, reducing the packet length. Okay, reducing the quality of the audio as well, obviously. Okay, so this is actually much faster, but the overhead now is, well, actually probably the same percentage in the beginning, but grows less because most of this was just initial cost. Okay, so what have we done with the Oki from, given the first implementation? Well, we've used it in the Oki Corral, which is the Oki, the protection scheme offered by the Oki. Something that looks like Click, but is actually a little bit more elaborate than Click, developed at MIT, called the Corral. And actually, we had a number of experiments which involved some active networks in user space with that. But ignore the active networks here. So the idea is that we have a number of elements which we can click together. They have push and pull operations. In the Corral, they can be either in user space, kernel space, or both, or even on remote machines. And we just simply click them together to form, I don't know, your favorite monitoring application. Now, this interacts very cleanly with normal C code. Okay, so we might have your general framework sitting here with packets received at a packet entry engine element, whatever you want to call that, packet entry element, and pushed to a packet exit element. And now you, as a third party, can come between those two elements, break the link, and reconnect it to your favorite monitoring application, so it runs in kernel space. Okay, fully protected by the Oki. Okay, this currently sits on top of Linux NetFilter. Okay, the application that sits in user space can then, using the same sort of elements, pull or push to kernel space. Okay, the other thing that we did a study for was, can we actually apply this to network processors? Can we apply this to even lower level processing environments? Okay. Now, whether or not this is going to be part of Scampi, I'm not sure, but it's definitely. I think it's an interesting study. So we have three main levels that we have to protect. Okay, we have the kernel on the host CPU. We have, in the case of an IXP 1200 network processor, we have a general purpose processor running embedded Linux on the card, and we have microengines, okay, on the same chip as the general purpose processor. Now, these things do not run any operating system whatsoever. Okay, so we've tried to provide the same sort of mechanisms for code running on the microengines as in for the rest of the processing hierarchy. Okay, so now the way we've done that is by having basically a stripped version of the Oki, because these microengines also do not provide things like stacks. Okay, so you can't have recursion, so we do away with that. And they have to have a different type of timeout protection, so the processing time protection. Why? Because these are no longer shared processors. Okay, these things are shared processors. Multiple applications run on the same host processor, but these things might be dedicated to a single application. Okay, so we've done a study as to whether or not this was possible and I will not go into detail. I'll conclude this high-level overview of the OKI by saying that, in my opinion, the OKI may form a basis for resource control, even when there are multiple mutually untrusting applications. Okay? It provides the resource control if required, but will not incur any overhead if not. Okay? The authorization procedures might be used, fairly simple, fairly straightforward. May be used anywhere within the Scampi project where anything needs to be authorized. And the overhead, even if all the runtime checks are added, can be very small. Maybe 10%, 15%, 20%, who knows. This is, by the way, the measurements that I just presented were using a very, very old version of the Cyclone compiler. This was 3 versions before the current version. Okay, the disadvantages are that, if you do runtime resource control, you will incur runtime cost. And another disadvantage is that the actual writing of these environment setup codes is a complex thing. So this is why this should probably happen once and can be used for multiple user groups. Okay, a number of APIs that could be used in the Scampi project. You can set authorization credentials, specifying your keys, and you can have 2 functions, 2 operations, which allow you to load or unload code from specific areas in your processing hierarchy, which might be your IXP. The location might specify IXP, a general purpose processor, and et cetera, et cetera. Okay, that's all for me. I'll be happy to take questions, if there are any. Any questions, or are we all dying to get to dinner?
Dinner's in 2.5 hours, I guess.
Okay, dying to get to the
So
pub.
there's still time for questions. Well, if there's if there's no questions, then I'd like to just say thanks to all the speakers who gave presentations this afternoon. That brings us to the end of the workshop, but I'd just like to mention that I'll put all the presentations up on the Scampi website, and I'll put a link on the front page. So if you're interested in seeing the presentations again, just go to the Scampi website, www.ist-scampi.org, and you can find them all there. Okay, just remind you that the gala dinner is tonight, starting at 8 o'clock, and that is being held in the Grand Cafe in the main square in the town centre. You can almost see it from here, but I'm sure there'll be a large group of people walking over there, so you can just follow them. And with that, I'll close the workshop and hope to see you later this evening. Thank you.